Let's get started. So, before I say anything else, please throughout the session use the chat function to send questions in. Okay, the three of us can talk cold spray for beginners for the next 45 minutes, but it's actually just a lot more enjoyable for everyone and more enjoyable for us if you can throw Stephan and Darren some really tricky, difficult questions. And I will enjoy watching them squirm and answer them. So please use the chat function. Welcome along. This is the fourth webinar that I've hosted for Speed 3D this year. Last month we did Right to Repair. So that was all about using deployable advanced manufacturing for defense and improving ground line of communications and supply of spare parts. For our final webinar of the year, our festive webinar, we're just going to do cold spray for beginners. So if you are a cold spray guru, you may be a little bit disappointed in this presentation because you'll know everything we're going to talk about. You're welcome to hang around and throw some questions or even make some good points yourself in the chat. But we really want to do cold spray for beginners because we are, as much as we love it, the three of us, our Speed 3D guys, we're not a very well-known way of making metal. So we thought we would do cold spray for beginners. So you're most welcome. Let's do introductions. So we'll introduce the team first of all. For those of you who haven't met me or seen me before, that's me. No, that's me. Calum, I'm based in the UK where I worked for Speed 3D. I'm basically an apostle. My job is to go around the world telling people how wonderful cold spray additive is. That's not cold spray, but rather cold spray additive, how wonderful it is and how useful it is and why people should be buying more of it. That's my job. I make little disciples and I help spread the word. I do that from the UK. Obviously, before I introduce my colleagues, Speed 3D is an Australian-based business with offices in Europe and the United States. Today we have two Brits and a German on the call, but we have an audience that currently, as I look at it, are India, Africa, Europe, and the United States and Canada. So we're doing pretty well for our reach. And don't forget, if you're doing your ironing right now or doing your sock drawer, then you can watch this again on demand. Over to my super panel, my superstar panel. Darren, why don't you unmute yourself and introduce yourself?
So I'm Darren. I'm a application engineer with Speed 3D, but previously I spent 25 years in the British Army, and I bring a slightly different perspective to the additive manufacturing industry. I think more about deployable additive as opposed to factory-based additive. But cold spray is cold spray. It works pretty much everywhere, and I'm happy to answer any questions you have today.
If I were to introduce Darren without him doing it, I would say Darren is a super user, particularly for defense. So when you put him in the defense environment with our equipment and say, can you make these parts? He's the guy that always says yes and gets after it. And so there's probably no one more qualified in making cold spray parts. Very few people in the world who will be as qualified as him at making additive parts with cold spray. To our next superstar panel. Out of Germany. It's not quite Aachen, Germany, is it, Stephan? Introduce yourself, tell us where you're from and what you do.
Yeah, thanks, Calum. Yeah, it's Aachen, so West Germany, close to the Netherlands and Belgium. Hi, I'm Stephan. I'm working as well for Speed 3D, heading the business development. My background is mainly automotive, but working in the additive manufacturing industry for 15 years already. So happy to answer all the questions coming up as well. Personally, I'm hunting for killer applications for Speed, mainly supporting customers in implementing cold spray for the applications, and not just technical wise as well in terms of economics. So happy to be here and, yeah, as I said, to answer later on some questions.
So at the end of this, if someone's listened and heard about cold spray and thinks, I've got an idea how this could be used in my world, then Stephan's the man to speak to. Stephan.Ziegler@speed3d.com. You can see his name there. And And then Stephan's here for another reason. He is my secret inject, because Stephan has spent a lot of time working with lasers. And I love comparing cold spray against lasers. And don't get me wrong, lasers are cool, right? Laser powder bed, wonderful stuff, does amazing things, but Speed 3D is different, and I like to highlight the differences. But I don't know anything really about lasers. That's why we bring Stephan along, Dr. Stephan, to give us some credence and some professionalism. Anyway, so that's us. Darren is in control of the slides, because this is a no expense spared, well-rehearsed production. There we go. So the first thing I'm going to say, we are, Speed 3D are a member of America Makes. And Darren, you can move on to the next slide. And don't forget, everyone, use the chat or the Q&A. In fact, I would really appreciate it if someone who is here watching from the outside were just to use the chat. Just give us a thumbs up so we know that it works. And Stephan can monitor that, because otherwise I feel like I'm talking into space. So Speed 3D, a little bit of business. Who are we? We are, Connor, you're a star. Thank you very much. Who are we? What are we? What do we do? Why do we do it? Speed 3D are Australian. Our founders, two founders, are based out of the big cities, Darwin and Melbourne. And they started the business almost 12 years ago now, in their garage, looking and designing a manufacturing process for the future. They came from a manufacturing background. They've been very successful, sold their business, and wanted their next project. And they landed on cold spray. They decided that it was actually the quality method, the economical method, the method that hadn't yet been discovered. Cold spray existed, but harnessing it to make metal parts, they decided 11 years ago that's what they would go after. We are the only cold spray printer. So that's not to say there aren't other cold spray companies out there, but they do cold spray guns, as I understand it, and I don't think I'm wrong, whereas we have the automation and the control that allows us to make parts. So the print file is created for you, allowing you to build actual parts and not just coat with cold spray. So we're the only ones in the world that do it for now. Someone will jump on it one day, I'm sure, but right now we're pretty unique. Spread across the world. The headquarters is Australia. You have teams like this in Europe, and you have even more of a bigger sales team, marketing and support team in the United States. We are known, as you can see from the image there, as the defense guys, which has been very good for us over the last 5 years, because defense have a real, the value proposition for defense is very strong. But it's not all that we do, and nor should it be, because cold spray makes high quality, repeatable metal. And so it really should be for industries well beyond defense. But that's where we've had our success. It's been our little niche. And you can see there, we have almost a follow the sun customer base all around the world. Aim for today, we'll do another half hour of cold spray, and we'll do some chat, and we'll do some questions towards the end. And if we run out of things to say, we'll just stop early and give everyone else 15 minutes of their day back. So if you're still with me, if you're still listening, this is excellent. This is it. We're about to go into the meat of it all as to what is cold spray. And this doesn't take long because it's really simple. Next slide, please, Darren. There we go. So Darren's clicking the video. So if we take metal powder, and we're talking pretty much the same metal powder that you will use for traditional metal additives, so for your laser powder bed stuff. If you take that metal powder and you move it really fast, and I mean really fast, 2 times, 3 times, 5 times the speed of sound, if you can move that metal powder really fast, eventually once it makes contact with anything, it's going to stick. Now, there's lots of things there you need to control. You need to control how fast you move the powder. You need to control the size and shape of powder. You need to control what it's hitting, and you need to control how you move that powder. And these are the different things which Stephan and Darren can talk about and how it affects the quality of metal. But all we're doing is moving powder really fast. The beauty of Speed 3D is that we stick that gun on the end of a robot, or indeed we have a static nozzle, and we control where it's pointing. So rather than just pointing, if Darren plays that video one last time, rather than just continually spraying metal like that in that direction and creating a great big puddle of metal, if we now start moving that, in fact, Darren, could you stop sharing the slide screen and then I can use my hands because I like to give a little demonstration. So if we've now got metal moving really fast, let's say from a static nozzle, because the printer behind me and the printer behind Darren use static nozzles. That powder is now coming up out a static nozzle. If the plate that it's impacting on now moves, we can build that part on the plate. So it's now just a matter of having controlled continuous flow of metal powder and then having the software to create the instruction for the robot, and the metal powder sticks and you build that part. That's for that printer that's behind Darren and the printer that's behind me. The printer that's behind Stephan, which makes much larger parts, the printer behind Stephan called Titan makes parts up to 2,000 kilograms. That, this time now, is actually a robot with the nozzle on the end of it and is spraying under instruction. And that big turntable on the floor that Matt in Australia is smiling beside, that stays relatively static. We turn it about a bit, but in essence, we're spraying. And so if we do that, we're able to build high quality metal. Now, the amount of metal that you're cramming in on that static nozzle or through a robot is really important depending on the types of metal. Okay, so the denser the metal, the harder the metal, the faster you're going to have to move that metal powder. Okay, and probably the greater the risk. You're going to have to control it to a greater degree. But the beauty of all of this is there's no melting. Why is it called cold spray? Well, there's no, let's call it deliberate, intentional, or melting of any worth. To the point that it isn't melting that's having this metal come together. It's the kinetic energy. We can do post-printing heat treatment on the metal, absolutely, but we're never melting it because it's liquid phase sintering. It's pre-melt points. So we're now able to create very fast these large metal shapes. So, depending on the metal, 100 grams a minute, 50 grams a minute, it depends on the metal. But it's really fast, meaning that you can make metal parts. Here's a metal part, right? This isn't actually one we've printed. This is one that we're working on. But once we start designing that and printing it, that's an hour print, maybe something like that, an hour. So you can make, and this is probably 1.2 kilos, I think, if I'm weighing it right. Maybe an hour. So we print really fast, which has lots of advantages because then it becomes economical. Different types of printers that you see behind us do printing at different sizes. The one behind me and the one behind Darren, they print parts up to 40 kilograms or a meter in diameter. But the technology behind the printers and what's involved is all the same. It's just packaging that makes it bigger. Darren, could I ask you, we don't need the slides for this, could you talk about what's in the background behind you there? We've got a printer, but we've got other stuff as well that you require for cold spray to be successful.
So I'll try and get out of shot. So in the center, we have the big printer. This is where you have the robot arm, the rocket nozzle, and the control of the pressure of the gases that are creating that kinetic energy that causes the impact, which is like bugs on a windscreen, just deforming that metal in order to stack them up. And then you'll see this way, like that way, the compressor in order to give that feed into the pneumatic panel. That gives us the gas. And in this case, we're using nothing but fresh air on this particular printer in order to give us that initial pressure. There's a heater inside the printer itself. We have, Get my fingers right. Dust extraction.
It's inverted, Darren. Yeah.
Yeah. Dust extraction. So we pull, we have the printer inside the chamber is all at a negative pressure. So we've not got any powder being forced out because of the pressures going on there. Everything's being sucked in and filtered through a water filter in this case, or in Calum's printer that he has behind him, it's a cyclonic filter. And then what you see behind the printer is the powder management. We call this a powder feeder, so we can accurately meter the powder that's being introduced into the gas stream through the rocket nozzle to create that deposition. So 4 parts packaged in different boxes inside this commercial variant. And what we've done with the X-Speed that way is push all of these into one 20-foot ISO container to make a field deployable. But they do the exact same thing. It's the exact same rocket nozzle, robot arm, the same build parameters, characteristics. It's just packaged as a deployable containerized version with those 4 elements together.
I want to talk about the software as well, Darren. Before Stephan, I'm going to come to you in a minute and talk about airflow and how that impacts metal and using different gases and the trade-offs. Before we do that, Darren, do you want to talk software? Because I guess that's the other crucial part of Cold Spray Additive.
So this is how we demystified for the end user making things in Cold Spray is the software. And we have a package called TwinSpeed. And TwinSpeed is a slicer and a G-code generator all in one. So we're using standard CAD formats, STLs or step files. We upload them into our software. It slices it exactly the same as Cura or Bamboo Lab. If you use an FDM printer, slices it into layers, and that gives us our individual layers that we build up. There are certain design limitations because we're using impact in order to build up each consecutive layer. You can't print into fresh air. You need something to impact into. So we have a 45-degree angle overhang limitation. You can build rafts in there, but we have a full software package where you basically drop an STL into that. As long as the STL is printable, it will slice it and it will deliver the G-code. You take that G-code, put it on the printer behind me, and it's just a couple of clicks, put the correct powder in the powder feeder, and away you're printing.
Thank you, Dan. Nice job. Stephan, talking about moving this metal powder quickly in different types of gas streams and the impact it has. Can you talk about that?
Yeah, sure. So as Calum already said, the carrier gas actually has 2 to 3 functions. The most important function is, of course, the acceleration of the powder particles to get it up to multiple supersonic speed to have that high impact Darren talked about just before. But at the same time, we are using the carrier gas to add some temperature to the particles. So I know it's cold spray, but it's not really cold. So we go up to certain temperatures, up to 800 degrees C, for example, and that is the second function. And then, of course, by selecting quite carefully the right carrier gas, you can as well have an impact on the oxidation behavior of the particles within the process itself. That's something, of course, depends on the laws, but you can see it quite nicely on, for example, pure copper or as well on titanium powders. But selecting other carrier gas than air is helpful to get the material a little bit softer, for example.
So I guess the 3 printers behind us at Speed 3D, as standard, the carrier gas to move our metal powder is just room air, okay? And that allows us to print certain alloys. What's the advantages of just using room air?
It's really easy. So you do not need any further supply on shielding gas like nitrogen, for example, or some further equipment. And if you're talking about the point of need producing parts in field for the arm process, for example, air is always available. So it's really easy. And the technology behind, so the compressor is state of the art. So you can find it everywhere. Actually, you can maintain it quite easily as well. So that's something which makes the whole setup quite easy to use. But of course, all the advantages come as well with some disadvantages, and that is finally the mechanical properties of the sprayed materials. That's the reason why we do, for example, for certain materials as well, like a heat treatment afterwards to soften the material. That's the case for pure copper. But in general, air is pretty well for spraying all over the world in all conditions because it's always available.
Good point. We're talking about heat treatment. Darren, give us a rundown. Talk us through the process: design, print, and the heat treat. Talk us through what it would be like if you're a user of one of these systems. You've had training from Speed 3D and you've been using it now for a couple of months. What would you expect to do to make a part?
Yeah, so as I alluded to earlier, there are certain design limitations. You can't print into fresh air. So what you need is actually a printable file, whether that's pre-prepared by maybe an OEM, or whether that's prepared by yourself. You just need to understand what the design limitations are, and we have all of this within our customer portal in order to give you a successful guide on how to design for Cold Spray. Design your part and export your part as an STL file. You put it through the TwinSpeed software, which I already spoke to, and then you upload it into the printer. The printing is really the easiest part out of the entire process. It's, the software interface is a couple of buttons, pressurize the system, load the part, put the substrate on, and press play. That is literally the steps of printing. Once the part's done, you take it out. And we talk about heat treatment. So heat treatment works differently depending on different material types. So for aluminium, for instance, it might require a two-stage heating process, because the first stage is relaxing the part and then causing a greater agglomeration. So we're already at 98.5, 99% dense, but actually we can get that a little bit better with the relaxing phase. If the material is a material that anneals, then we need to probably put in a second stage where we harden it back up to the material properties that we want. If it's a material like steel that doesn't anneal the same way, then it's just a single stage process. But we're using the heat treatment almost just to refine the material properties. So at the back end of the process, the material that's printed is as you expect it and as we publicize. And we can use hardness testing in order to clarify that the heat treatment has worked in the way that it should be done. And there's also a flowchart within our heat treatment processes that if you overshoot or undershoot, you can recook at certain points for certain times in order to refine those material process. So there's lots of checks and balances throughout the process in how we print. And then the final part is just, we produce things near net shape. So imagine something coming out of a sand cast. So you have the rougher surface finish. You have a few bits and pieces that aren't the fine detail you need for the final part. The final part is just machining those critical surfaces, critical dimensions in order to make the final part. Much the same way that a casting house and a machining shop will for an off-the-shelf spare. It's something that we talk about quite openly and honestly. It's heat treatments and machining and post-processing. Other people put it in their fine print, but they don't openly talk about it. So we see ourselves as a three-stage process, and we print, cook, cut, and then you've got your part at the back end. But the beauty of the system is, because it's so quick in the printing portion, the heat treatment, although it can be up to 12 hours depending on the material, actually is probably still quicker than an alternative that's taking hundreds of hours in order to print a larger format part.
Thanks, buddy. Stephan, one for you. And this is probably a Darren question, but he's just been on for a couple of minutes, so I'll give him a break. So for background, Stephan's been with the company now a year and a bit.
Yep.
And taking these printers out into the field, deploying them in the field, so like the one behind me, which is portable, you get to do it every so often. And certainly most people haven't taken a cold spray printer out into the middle of the jungle, into the desert as we've done, Africa. We've been all over with these printers. Darren's done it many times. For you, Stephan, compare taking cold spray around the world to compare taking laser systems around the world, because this is why I love it. Talk about what it takes to move it around the world, set it up, and then change the metals so we can then print different things.
Compared to all other additive manufacturing technologies, it's really easy. So we did it a couple of times for the European roadshow, I'm getting now used to it as well. So I would say it's roughly 30 minutes from drop off till we are fully on the operations. So
what does that mean? Paint a picture.
Yeah. So the lorry arrives. Normally we have, besides the printer as well, a second container with the post machining and heat treatment equipment with us. So the lorry or the truck arrives, has both containers on the back. The lorry or the truck has side lifters taking both containers and just dropping them where it's needed in front of the shop floor or in field. And what we're doing then is actually we're just plugging in the X-speed to the generator to power it up. Of course, preparing and removing all the fixtures from the powder feeder and from the robot arm, which was stored for transportation to avoid any damage. And for the second container, it's actually just powering up, opening the doors, and doing the same for the CNC and for the furnace, so removing the transportation fixtures. And then actually what we're doing then with the cold spray equipment is just putting in the powder and printing a calibration block to check if everything is running quite smoothly, which takes a couple of minutes. And if needed, we adjust then the parameters slightly to get really close to the required shape, to get a really near-shaped parts producing. And that's it, actually. So
quite simple, right?
So Darren trained me within, I would say, 1.5 hours to bring that piece of equipment into operations.
So
just once.
Training someone in an hour and a half to get up and running. The system behind me, X-speed, you can move around the world, drop on the floor, plug in the electricity, feed it powder, and if you're Darren, you're up and running printing in about 45 minutes. The system behind Darren, which has obviously got subcomponents, they're all, can pick them up with a forklift and move them around your facility. That's going to take you an hour or two, maybe max, of hooking them back in together and then doing the calibration on the warp speed on the printer itself before you start printing. Point is, cold spray is ruggedized because it's not using the lasers. It's just solid state. It's just moving metal. Changing powder. I get this question a lot. I'll look at the question there in a moment, Stephan, or if you read it out. Changing powders really quick. So what does that mean? Well, 1 minute you can be printing aluminium. The next, if you want to change, 15 minutes to 30 minutes to change out the powder and print again. I'll say that again, 15 to 30 minutes is really quick. That gives you, the customer, the ability to print cool stuff and not have to wait a long time to do it. So if you want to try different metals on different metals, you can do. So it's really very useful. What's the question, Stephan? Am I going to like it? Is it difficult?
What is the max deposition rate for the CSAM equipment? So I answered already online. Depends, of course, a little bit on the material, but it's up to 100 grams per minute with our current setup.
What does it take to increase it?
More pressure, finally more energy. That means more pressure, a bit more temperature. Currently we spray about 30 bars in our conventional setup.
Yeah, and there are the other cold spray systems out there, arguably, there are other systems out there printing at higher pressures. So it's absolutely doable. It's a matter of work. And doing so will open up the range of materials that we also print with. Let's talk about some use cases and some printers. Great question, Lucas. I'll get to that whilst, Darren, if you bring up the slides and take us straight to the kind of use cases. Lucas, you asked what the materials that we print with. So copper, aluminium 6061, there's nickel aluminium bronze, there's an aluminium bronze, there's a stainless steel. What am I missing? And that's a 316L. So and these are materials which we are guaranteeing, for want of a better word. Never say guarantee, but these are our accredited materials. So if you use the powder to a standard of powder that we specify, if you stick to that powder, if you print the way we tell you to print, then you will get the results that we tell you you're going to get. But it is not a closed system. So if you want to, like many of our customers do, experiment with powders, you're freely able and capable to do so. You don't need to buy your powders from us. You can do. That's brilliant. We make money doing so. But you're more than welcome to go source powders from other powder suppliers, giving you the freedom, flexibility of choice and cost, and the ability to then go and experiment with different metals. And lots of our customers do that. And it's a great selling point for Speed 3D.
Oxidation behavior, because that was the second part of Luca's questions.
Okay.
Let's take copper as an example. If you spray it with pure air at 30 bar, you end up with, so I'm not sure about the amount of oxidation, but what you can see is it gets quite brittle. It will be around 1 to 3% of elongation at break. If you do the heat treatment, you can double it, maybe triple it. So you're ending up just below 10% of elongation. If you change then, for example, same setup, just away from air to nitrogen, you end up with 18 to 20%. And if you increase then the pressure up to 60 bar, you end up with 20 to 25% of elongation. That's what we can achieve, for example, with pure copper.
Nicely done, Stephan. And as you were answering that, I could just feel the panic in Darren as he was trying to get that presentation to jump up. But yeah, to answer the question, and then the kind of performance of the materials, Lucas, if you print with our system on our standard materials and you use a standard heat treatment, you are going to get a metal that performs about 20% better than the cast equivalent. That's generally whereabouts where we fall. So we're not talking the performance of a rock metal. This is all about replacing cast metal parts, and our metals generally perform about 20% better than cast. We can, if we go to the next slide, please, Darren. Right, so let's talk about, let's talk about what parts look like. In fact, the image on the left-hand side is a really good one. So let's talk about the patient. The patient was the Bradley fighting vehicle that you can see in the image on the right-hand side. Speed 3D were challenged. In fact, Darren was challenged to train a US soldier. Darren can correct me at the end of the story. A US soldier in, I think it was 2 days, to be an advanced manufacturer. In that, they had to design a part, print a part, and machine a part after 2 days of coaching. And it was for the Bradley fighting vehicle. It was the part that you see here. It was a mounting bracket that holds down the transmission system. And on the very far left, you can see the green image. So the soldier has designed the part on our software TwinSpeed. And not only when you design the part, do you create a print file, but you also get a full digital simulation. And that digital simulation will tell you if you're going to be successful or not. So everything in that image is green. That means what you've designed, the printer can achieve and will achieve. What you see in green is exactly what you see in that middle picture. If, however, we designed a part that was beyond the printer's capabilities, you got one of the design rules wrong and you did something that's just beyond its capability, the angles don't work, the simulation will show blue. Okay, the printer will show you where it's tried to achieve what you've wanted, but failed, and it will be in blue. Meaning that when you print something, you're only printing generally, unless you're tapped, you're printing when everything's green. So you know that whenever you print, you are going to be successful. Okay, and it's an automated process, it's a reliable process, and I mean this when I say it. That green image is what you get on the out. It is super reliable. The simulation is bang on all the time. And you can see there it's 2.5 hours to print that part. The heat treatment for that was 11.5 hours, and then 2 hours of cutting. So if you're in the world of the military, that's under a day to have that part turned around for you. That part was then fitted to the vehicle and driven around the test area to prove that what we make is serious metal. But to Darren's part about we make near net shape parts, you can see exactly what we mean by near net shape. Now, the team there have obviously done a terrific job at machining all those surfaces. Not necessarily required on everything that you make. You get many pressed metal parts where only some of the surfaces are machined. You then give it a lick of paint, and the part is ready to use. In this instance, just to demonstrate and to give confidence to people that what we make is serious metal, we've machined all those surfaces, and they look beautiful. Darren, you were there, you were doing the training. Is there anything I've missed out?
No, you covered pretty much everything there. So when we say the simulation's pretty close, even the texture on the top of the simulation on the left-hand side of the screen is repeated on the texture of the printed part in the middle picture. So down to surface texture, it's pretty much bang on what you expect to see at the back end. And if you look in the right-hand picture, the soldier in the turret is the actual soldier that I trained, and that is the vehicle driving with this part fitted during the trial in Tennessee. This guy was an absolute additive manufacturing skeptic. Turned up and he'd been in the Tennessee National Guard for 20 odd years. And he was one of these people of never needed it before. If it ain't broke, don't fix it kind of people. Within 2 days of getting his hand on this technology, he's like, I need to learn how to do CAD because this is the future. This is how warfare is going to be fought in the future, how logistics are going to be, fulfilled within a contested environment. Within 2 days of using the system, he went from being this absolute critic of everything to almost an evangelist, preaching it to every single person that he could. And he had no additive manufacturing experience at all. So it shows how quickly you can pick up, with the correct guidance and a little bit of prodding in the right direction. A soldier that's a skeptic can produce a part that's making that Bradley fighting vehicle back in the fight.
If you go to the next slide, Darren, maybe the video will work and we can see the part being printed. Oh, look at that. Seamless. What a seamless production. You're in the wrong job, Darren. So middle video, although it's a bit, there's a bit of reflection there, you can see the part. That's the speed the printer moves at. So we've not sped that up. That's the speed at which the robot arm is moving. You can't really see the powder being deposited because it's moving too quickly. And on the left, you can see the part fitted to the vehicle. And on the right-hand side, Darren, I can never remember why we've got 6 different parts there on display.
We demonstrated in the different materials that we had.
Ah, right, okay.
If you see at the very end, we've got nickel, aluminium, bronze. There's a couple of aluminium ones. There's a stainless steel, and the chrome one is the original factory painted.
Yeah.
The original part was aluminium, but we just wanted to demonstrate that you could repeat the geometries with different materials. It has different print parameters and times and heat treatments, but you could produce this in a variety of different materials. It just so happened that the aluminium was the case that fit the bill in this particular application.
Wicked. Let's go to, there's a question in Q&A, which is a good one. I'll do first bit and then someone can help me with the second bit. What's the protocol for unspent deformed powder? Can it be reused? And then it goes on to especially for reactive alloys like titanium. So the answer is, what appetite for risk do you carry? So you can, when you print with the system, there is obviously an amount of powder that doesn't stick. Depending on the powder you're using, the softer the powder, the higher the deposition success. I'm just going to change my view so I can see everyone. And as we're depositing, powder sticks, some of it doesn't stick. And inside all of these systems, there's a vacuum system that's pulling any unused powder down and out into a dust extraction system. Now, if it's the printer behind me, that's a dry cyclone system. And you will come away with a cup of unused metal powder. And would you want to use it again? Question is, why? Is it cost? Okay. What's your appetite for failure? Because you can use that powder again. You can stick it back in the system. But I'm going to argue, and we don't do a lot of this, but it has been done a good few times by customers, that powder will go through the system and you'll get probably a lower percentage of deposition success with the reused powder. But if that's the only powder you've got and you want that part made, depending on the environment you're in and the sort of industry you're in, that might just be what you're willing to do. If you're in the world of high engineering hygiene, it might not be. You talk about titanium when it comes to reusing it. The answer is I don't know. I don't know if the guys in this call know. Reusing titanium. Titanium's, we have customers that print titanium. You'll notice it wasn't one of the metals that I mentioned as a stock metal, that, you know, one of our regular alloys, but we do have customers that do it and have developed that on their own. As to reusing it, I don't know. And I can't remember the rest of your question. The as printed porosity, I don't know. Is heat treatment or HIP mandatory? Right. Okay. So if we put titanium to one side, we'll come back to it. Is heat treatment mandatory? No, it's not. So we have printed many parts and used them without heating them. When you print, you are basically making something that's a very strong coffee cup. It's strong, but it's brittle. We have made many parts which, because of the job it's going to do, frankly, it doesn't need the heat treatment, and time is more important. So you're still getting a strong metal. What you need to be careful of is that metal able to be cut without the heat treatment? Some metals are able to be cut without heat treatment, some are not. So sometimes yes, sometimes no. With regards to titanium, can you print that without heat treatment? I've no idea. Do you need to HIP things? No, you don't need to HIP things. Certainly, we don't HIP things as a matter of course. But when we do know, because we've done a lot of work with HIP research, when you HIP our materials, the performance of the materials go through the ceiling, right? So you then are talking about making materials that are performing at the ROT standard. But HIPing, you know, there's no point in having a deployable machine if the thing needs HIPed. We mentioned we have speed felt. That's the container that goes along with this. It's just another green container with the standard air furnace that you would effectively sinter your parts in. You put it in the oven, you pull it out, and you quench it in a bucket of water. Doing that gets you your cast strength or above metal part. Kind of danced around titanium there in different answers, guys. If you're reading the question, feel free to add any more, because it's a really good question.
The porosity,
yeah. I don't know.
Porosity will be, it depends slightly, but I would say it will be something between 1 and 3-4% in the worst case. You can tweak it probably to much better. But in general, the process is quite dense, always quite dense. So that's the nature of the impact, having dense parts. HIP is not mandatory. Heat treatment, I would say, technical-wise, especially the structural part, it is mandatory. You need to do the heat treatment for Ti64. HIPing, no. And there's actually, besides the heat treatment part of the HIPing process, there's no reason why you should HIP it, because the porosity is already quite low from my point of view, especially if you have a pretty well optimized process.
Cool. I'm looking at the time. We've kind of done 45 minutes of us speaking. Thank you for the questions thus far. We've got some minutes left to throw in questions. I don't think there's more information which really we're going to share on the call. What we can share in the slide deck is more examples of parts. Okay, so the sorts of things that we make, which we can start showing. And we can do that as you throw in some questions. So we will spend the rest of the presentation just showing the sorts of shapes and parts that we can do, and you can keep throwing in your questions, which is terrific. Stephan, can you look at the questions, mate, and I'll talk about parts.
Yes.
Darren, can you go forward 2 slides, please? one more. Nickel, aluminium, bronze. So Cold Spray loves copper-based alloys. Okay, it is the sweet spot. But I like this slide because those parts look cool. And they look nice and shiny. And it gets to talk about nickel, aluminium, bronze, and what a great material it is. You know, for myself in the defense world, we are in the defense world. It's all about how many submarines and how many ships can we make, and how do we get access to making these complex metal alloy systems. And so we have been working a lot over the last 2 years at developing those sorts of materials. And whilst you can see microstructure there of what we're calling expeditionary nabs, so that's using our basic heat treatment. If you hip this stuff, the properties go beyond drop, which is incredible. But if you're looking to do this on the side of a shipyard, then you might just want to do the basic heat treatment. These parts here have had the basic heat treatment, and they are awesome looking parts, and you're able to make them very quickly. Stephan, what's the questions popping in? I saw them. Shall we quickly cover a question and then we'll show another part?
In the chat, Lucas asked if you see as well some improvements on aluminum and stainless steels if you're using nitrogen. We'll see some improvements for aluminum, not the same amount in ductility, especially like compared to copper. Stainless steel will be much less. Going from air to nitrogen, there are other mechanisms which are stronger, like particle bound and so on. Then we have a question in the Q&A. What impact porosity of the part that is made by the process? I'm answering it currently. So from my point of view, it's mainly the process parameters, feeding rate, temperature, and the pressure, as well as the material, the PSD. So cold spray is quite sensitive to the right PSD, so particle size distribution, sorry, and the chemical homogeneity of the material. So if you have for example, hard phase particles in the Ti-64, there you need more energy to have the deformation. Yeah, that's something you normally try to avoid. So these are the parameters, but maybe Darren, anything to add on that?
No, that seems to have covered it.
The questions are fantastic, team. Thank you. Charlotte asks, what are the overhang limitations on the Titan with a moving nozzle? Darren, you're the only one that's really worked on it. Have you had a chance? Have you even learnt that?
Yeah, so it's pretty much the same as our other system. So we can get to 45 degrees with a small caveat. So you couldn't build at 45 degrees directly from the build chamber, the build surface, because the way the angle of the nozzle needs to come in order to do an edging path. But it can still do 45 degrees. And probably actually once the software guys actually really optimize the software package for it, it probably achieve in excess of 45 degrees because it has more articulation due to the nozzle being on the robot, and it hasn't got the same limitation that the build plate has in moving around the nozzle. If that makes sense. It's hard to articulate this without being on full screen. But at the moment, you've got a 600mm build plate that needs to avoid the tower. So you can only get a certain amount of angles and positioning in retrospect to the nozzle.
Mm-hmm.
Whereas at different heights, the nozzle can technically come in.
Yeah.
But at the moment, rough ballpark, 45 degree, just not directly on the initial build plane.
Yeah. Okay. We'll keep going with the questions. Are you able to make a bimetallic part, say, using copper with Inconel cladding? Stephan, what do we think? Thank you, Sujit.
So
I love a difficult question. It should be done over an hour-long conversation. I'm trying to answer it in 30 seconds.
Yeah, it's a good question. So we could coat Inconel part with copper. That is absolutely feasible. Could we spray copper and Inconel at the same time? In general, yes, it is feasible with cold spray, but Inquinel is not a sweet spot material for cold spray in general. And for us, because we're just using one powder feeder currently in our setup, it means you need to change the material and then restart the print. So not really easy, but general would be feasible.
There you go. Lucas has got another one, but I'm not sure if I'm reading it right. I'm really interested in your slicer software. Good man. When we spray different materials, we always have different spray trajectory, and the next word I don't know, Roshan, for each material. For example, copper and titanium. Copper, titanium have different spray cross sections. Lucas, come back and just retype that, mate, and we'll try and answer the question before the end, because it doesn't make all that much sense to me, the question. Guys, you're reading. I don't know if you're reading it. Let's look at, Darren, let's just quickly flick through some parts, because that way we just get to demonstrate the size and shape of stuff. This one was an Australian patrol boat. That cam lock fitting, there are maybe, let's say, half a dozen of them on this ship, and let's say there are 12 of these ships in the Australian Army, and they're part of the fire suppression system. So basically, it connects a compressor to a hose to fight fires, but it was made of, if I remember rightly, the original one was made of 3 metals, dissimilar metals, and the thing would rust itself into its original atoms. It just fall apart. So we were challenged, what would you do if you were making it with cold spray? And we just made one metal out of aluminium, and you can see the print time there. Now, that's not what it looks like when it comes out the printer. There's some machining that's went into making that happen, but the print time's really quick, and the machining wasn't all that long. Frankly, you know, if you're doing that in under a day, you're doing pretty well.
I can answer Lucas's question. I think I get this. So I think what he's saying is different materials deposit in different manners. Actually, what we see with cold spray is if we're spraying vertically, everything ends up almost like a rhombus shape. So what we have is we have an edging path in order to give us those vertical walls as part of our slicing software. So the geometries aren't different, and the tool paths, the movement of the robot isn't different per material, because we can print in a predictable manner, and we have these edging paths as well as an infill path. So the way I like to describe it is, we use the term infill because that's the standard within the AM industry, but actually it's like a foundation path. You spray the foundation that you're building your house from, and then you lay the brick wall on the side. That's the edging path. And then you do the next layer of foundation and then the brick wall in order to give us our vertical paths. And this works the same on every single material, what we found with all of our experimentation and materials that we've used. So the tool paths are the same. Doesn't matter what kind of material we're using. I hope that's answered your question, Lucas.
If only there was a thumbs up function. Let's quickly just skip through some more parts, Darren, to give people an idea of size and shape. Australian Army G-Wagon alternator shield. The original one, I think, was made of plastic and was just getting trashed. 2.5 hours to print. Again, thank you. You nailed it. Well done, Darren, says Lucas. I won't go into every story because we've not got time, but let's just flick through it to show you the sorts of shapes and size of metal that we're talking about. That part there, so someone asked about, do you have to heat treat a part? So that part there, for that particular vehicle, it was a tool for getting a very large nut off. No heat treatment and no cutting. All we did was file off some of the edges with a hand file, and we were able to use the part. That was a specialist tool that the guys down in Fort Irwin could not get their hands on. You know, Fort Irwin's a big place. That tool did not exist in that camp. And had we had the time, had we been there longer, we could have printed dozens of them for them, and they would have loved us for it, because it's, you know, Darren knows when you can't get the tool you need. It's stuffed. Skip that, mate. There's not a lot. I want to try and get some images. We're going beyond what I'd planned for the presentation, but it's nice just to get these are the slides we can show. Keep going, mate.
In the meantime, a further question came in. Can you elaborate more on in situ environment? Does the temperature change with deposition? Build plate is at 500 degrees C, powders at 500 degrees C. Can the chamber be filled with inert like argon? Can the chamber in high vacuum?
So, yes,
You've got 30 seconds, Darren.
Yeah, we've had people try to inert the chamber. Actually, what we find the easiest thing to do is inert the gas stream, and the same as an arc welder, it creates an inert bubble over the area where something could potentially be combustible, such as titanium.
There you go. Swift answer. Right, we are ending on time. Always end with a, you can bring down the slides, Darren. Thank you. Always end with a call to action. You can see our names. We are simply darren.kitching@speed3d.com or stephan.ziegler@speed3d.com. If you have more questions or you want to follow up, just send us an email. But Aravind, Charlotte, Christopher, Connor, Evan, Hakim, Juan, Lucas, Marek, Miguel, Param, Renee, Robert, and Suji, thank you very much for staying with us for the whole hour. It would have been a pretty lonely call had you not been here. And if there's anything we can do for you, give us a shout. This was an amateur Speed 3 production, Speed 3D production. Thanks for joining, and we'll see you in the new year for a webinar that is yet to be decided. Thanks, everyone. Have a good day, and we'll catch up on the other side. Bye, everyone. Thanks, Darren. Thanks, Stephan.
Thank you.
Bye. Cheers.